Howdy, howdy. Welcome back to AP Chemistry. The video today is going to be about intermolecular forces, solids, and liquids. So the first thing that I want to talk about is the state of matter. So the states of matter depend on two things largely. That's the average kinetic energy of the molecules in the state, namely, what's the temperature and how fast are they moving, and also the intermolecular forces present in the compound. Those two things combined generally, or I guess most often, are going to be the determining factors of what's the state of the matter. Is it a liquid? Is it a gas? Is it a solid? So let's think about this. In the solid state, think about what the atoms are doing, what the compound is doing. Everything is always vibrating. There's vibration always happening as long as you're above 0 Kelvin. But there really isn't movement of those atoms and compounds around in the molecule. They're sort of stuck near each other. There's no translational motion. What that means is that the kinetic energy cannot overcome the intermolecular forces holding the atoms together. You have atoms, and they're next to each other, and they're vibrating. These little lines mean vibrating, but they're not moving around, right? They're staying in this sort of rigid configuration, but there is vibration happening, right? So that the forces holding those atoms together is too strong. It's so strong, in fact, that the kinetic energy, the movement of those atoms, is not great enough to overcome it. So they don't move. They're stuck. I mean, think about the table that you're working on. Everything's vibrating, but those atoms aren't moving around. So then we increase the temperature, and we increase it to such a degree that the kinetic energy begins to overcome those attractive intermolecular forces, and the substance will eventually melt. And what that means is that now, right, all the atoms are still really close together, but we've got now where they can move around, right? Think about a liquid. They're still vibrating, but now they have translational motion. So the kinetic energy is able to overcome some of those attractive intermolecular forces. Now, if we continue to increase the temperature, eventually we'll give these particles enough kinetic energy so that they're able to break free of the intermolecular forces. We think that for our class, when a compound is in the gaseous form, really it's overcome those intermolecular forces and is now able to zoom around like a gas outside of the liquid, right? So what we can do is relate that to a heating curve, which is something that we'll talk more about on Wednesday. But if we look at this, we'll see that on the y-axis we have temperature, and on the x-axis we're just showing sort of what the state of matter is. And this is a heating curve for water. And so everything below 0 degrees Celsius, I hope that you understand that means that the water is solid. Between 0 and 100, the state of water is a liquid, and above 100, we are in the gas phase, or we can think of it as a vapor. And so what's happening? We increase the temperature here. We're increasing the kinetic energy of those water molecules, and eventually we get to a point at 0 degrees Celsius where the average kinetic energy of those water molecules is high enough to where they start to melt. And then we have this horizontal line. And this is the melting process. And the temperature doesn't increase because all of the energy that's being put into the water is being used to melt the solid ice. Then, once all of it is melted, we have 100% liquid water. Then the temperature will start to rise again. And as the temperature rises, so too does the kinetic energy. And at some point, it gets so high at 100 degrees Celsius that the liquid water starts to escape the liquid phase into the gas phase, meaning those gaseous water molecules have completely overcome the intermolecular forces. Again, the temperature's not changing here because we are vaporizing, or you can think of this as evaporating, all the water. So all the energy that's being put in to the system right here is being used to convert the liquid water to the gaseous water. Then once all of that liquid water has been converted to gaseous water, so this is 100% gas, then we can increase the temperature again. Okay? The processes of melting ice and vaporizing liquid water, they have special names, and so those are enthalpy of vaporization and enthalpy of fusion. And that works going either direction, heating the water up or cooling it down. Same thing. So then let's quickly talk about phase diagrams. So the phase diagram on the left shows all the different words for phase transitions. So solid to liquid, melting, liquid to solid, freezing, liquid to gas, evaporation, gas to liquid, condensation, gas to a solid, deposition, solid to a gas, sublimation. And for all phase diagrams, on the x-axis is going to be temperature, and on the y-axis is most often going to be pressure. On the right, you'll see that we have the phase diagram for water. And there are three things actually, that I want to emphasize on this phase diagram. First of all is the triple point. The triple point is a unique moment at a specific temperature and pressure, right, where all three phases exist in equilibrium. That means that all 6 of these processes, melting, freezing, all of them, are happening in equilibrium at the same time. Okay? The second point that I wanted to point out is the critical point. And the critical point is where a gas and liquid phases are indistinguishable beyond that point, and no matter the pressure, the gas cannot be condensed back into a liquid. So no matter how high we raise the pressure and force those gas molecules closer and closer and closer together, we're never going to be able to get it back into a liquid beyond the critical point. So the critical point here happens at 150 degrees Celsius. So we would say that the temperature at the critical point is 150 degrees Celsius, which means anything higher than 150 degrees will never be able to get a liquid at any pressure again. Okay. Another thing that I wanted to point out is the slope of this line between the solid and liquid. You can tell something about a substance based on the slope of this line. Here, for water, the slope is negative, right? If you have a negative slope, what that means is that the liquid state is more dense than the solid state. On this phase diagram here, you'll see that this line has a positive slope. So it's exactly the opposite. A positive slope indicates that the solid state is more dense than the liquid state. And that kind of makes sense because as you increase the pressure, what you're forcing those molecules to do is get closer together, which means they're going to favor whatever state is most dense, right? Density is mass over volume. So if we're increasing the pressure, forcing all those atoms and molecules to get closer and closer together, they're going to want to be able to fit more atoms and molecules into the same amount of space, right? So what that's saying is that the liquid's more dense. We can fit more water molecules in the same volume as we increase pressure. Okay, so let's move on to intermolecular forces. The first important part about intermolecular forces is thinking about dipole moments and what those dipole moments are, what they mean. So polar covalent bonds will result in the presence of a dipole moment. And a dipole moment is a separation of partial charges. Partial charges, we use a lowercase, I think this is sigma. So we have partially positive, partially negative, right? Polar covalent bonds result from an electronegativity difference between two atoms. So the covalent bit of this means that there's still sharing of electrons. The polar part of this means unequal sharing of electrons, right? This is in direct opposition to ionic bonds where there is no sharing of electrons, right? You have ownership. So thinking about differences in electronegativities, right, here are a lot of examples of polar covalent bonds. So you want to think about what the electronegativity is of an element and what it's bound to. If they're different, right, it's going to be a polar covalent bond. And you're like, well, how do we know that? Well, carbon bound to nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, that's going to be polar. And then hydrogen bound to pretty much everything but carbon's going to be polar too. You can look up charts for this, but here are just some examples to try and help that be a little more intuitive for you. So let's look at a hydrogen chloride bond, right? There's a big electronegativity difference between hydrogen and chlorine. And so what does that mean? The more electronegative element means that it wants electrons. So more electronegative means that it wants electrons. Because it wants electrons, that means that more electrons are going to be spending more time on that atom, that element. So the more electronegative element's going to have the partially negative charge. The less electronegative element's going to have the partially positive charge because its electrons are being taken from it, or spending less time at it and more time on another atom. So whenever you have a separation of charges like this, and for us, these are separation of partial charges, that is when we have the existence of a dipole moment. Di meaning two, pole meaning charges. So we have two charges, dipole moment. I'd also like to emphasize the periodic trend for electronegativity. So as we move to the right on the periodic table, electronegativity increases. And as we move down the periodic table, electronegativity decreases. Okay? So part 2, types of intermolecular forces. So the first type is going to be ion-dipole intermolecular forces. These occur between an ion and one end of a polar molecule. Ion-dipole. So you have to have an ion. These types of intermolecular forces are especially important in aqueous salt solutions because the salt solution is implying that you have ions which dissociated into the water. So I have two examples here. I have a sodium cation in water and a chloride anion in water. So sodium cation is a +1 charged atom. And how is the water going to orient itself around the sodium? Well, oxygen-hydrogen bonds are extremely polar. There's an extremely polar bond. So you are going to have a separation of partial charges. Because oxygen is the more electronegative of the two, it is going to be partially negative. According to Coulomb's law, this partially negative and this positive, they're going to want to get together. Opposites attract, right? So the water is going to orient itself around the sodium cation such that the oxygens are pointing towards the sodium. The exact opposite is true for chloride anions. Here we have a negative charge. Here we have our partially positive. Water is going to orient itself around the chloride anion such that the hydrogens are pointing in the direction of the chloride anion. This process of water orienting itself around ions is how water solvates ions. It's also why water is considered the universal solvent because it has a partially positive and a partially negative side, so it can handle dissolving lots of many things that result in positive and negative ions. Okay? Ion-dipole intermolecular forces are often some of the strongest, most significant intermolecular forces. The next is dipole-dipole intermolecular forces. These result from the attraction between the positive end of one dipole and the negative end of another. So here we have gaseous hydrochloric acid. Why gaseous? Why not liquid? Well, because we know that HCl is a strong acid, which means that it dissociates 100% in water. So you actually don't have HCl bonds in liquid hydrochloric acid. Right, you have chloride anions and hydronium ions. But in gaseous HCl, we do have this bond. So here We have a polar covalent bond. I've drawn the partial charges. Chloride's partially negative because it's more electronegative than hydrogen. And how is this second gaseous molecule floating around going to orient itself? Is it going to put the partially negative chloride next to the other partially negative chloride? No, right? According to Coulomb's law, we know that oppositely charged things attract. So how it's going to orient is hydrogen to chloride, like so. Here is our dipole-dipole intermolecular force. In example B, we have formaldehyde. And you see here that we have a carbon-oxygen bonds. Carbon-oxygen bonds are polar. Carbon-hydrogen bonds are not polar. Carbon and hydrogen have almost the same electronegativities. So the question is, how are these two formaldehydes going to orient themselves such that we're showing dipole-dipole? So we have this floating around, ooh, right? Is the oxygen going to get next to the oxygen? I hope you see that that's not what's going to happen, because the two partially negatives are not going to want to get near each other. However, if it orients itself like this, you'll see that we have a partially negative, partially positive near each other. And so I put them too close, which is okay. But you'll see that there will be the dipole-dipole intermolecular forces. These are dipole-dipole intermolecular forces are often weaker than hydrogen bonding. So I'll write out a list of order of this, but so far it goes ion-dipole is the strongest, then dipole-dipole is going to be weaker than that. So hydrogen bonding intermolecular forces, a crowd favorite and one that causes lots of heartache and confusion, but it doesn't have to. So hydrogen bonding intermolecular forces are the exact same thing as dipole-dipole intermolecular forces. It's the same thing. It's just that these hydrogen bonding intermolecular forces are three very specific dipole-dipole forces, right? They occur between a hydrogen in an NH-OH or FH bond. So it occurs between a hydrogen and one of those bonds and any of the three atoms with lone pair electrons. So the first thing is that you have to have either a nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond. If you don't have one of those bonds, you do not have hydrogen bonding, right? That's what makes hydrogen bonding unique. These three bonds are extremely polar. So polar, in fact, that they warranted being given their very own name, hydrogen bonding, okay? And you're basically making a hydrogen sandwich between one of those bonds and one of the three atoms with lone pairs. And it doesn't have to be like F to H to F. It could be F to H to N to H to O, right? It doesn't really matter. It just has to be a sandwich between those elements. So the first one, example A, is probably the easiest, right? We have water and water. Here you'll see that we have an oxygen-hydrogen bond. Then you'll see that we have one of those three atoms with a lone pair. So we have nitrogen, oxygen, fluorine. Okay? So the hydrogen bonding interaction is going to occur here. Hydrogen bonding IMF is not the same thing as a hydrogen covalent bond. This is an intermolecular force. Intermolecular forces occur between two different molecules. Okay? Let's see. So then this green part here, this is what we would consider the proton donor. And this orange part here is what we would consider the proton acceptor. The orange part. Okay, let's look at example B. We have formaldehyde again. Good old friend, formaldehyde. I love formaldehyde. It's the simplest carbonyl compound. So carbonyls are functional groups in organic chemistry of a carbon doubly bound to an oxygen, if you're curious. So we have formaldehyde. And the first thing we need to check is, do we have a nitrogen-hydrogen, oxygen-hydrogen, or fluorine-hydrogen bond? No, we don't. We have carbon-hydrogen, but carbon-hydrogen bonds do not make hydrogen bonding intermolecular forces. So since we don't have one of those three bonds, we do not have hydrogen bonding here. It can't occur. It cannot occur. What we do have is dipole-dipole interactions, just like we did in this example. Okay. Example C, though, now has ammonia, NH3, with a molecular geometry of trigonal pyramidal, and a formaldehyde molecule. Now, can we have hydrogen bonding here? So first we need to check, do we have one of those three bonds, NH, OH, or FH? We sure do. Here's an NH bond right there. Then we need to see, do we have one of those three atoms with lone pairs somewhere? Nitrogen, oxygen, or fluorine? Well, we sure do. We have an oxygen with lone pairs right here. So what can happen is that this formaldehyde molecule can get oriented in such a way that it can also do hydrogen bonding here. Hydrogen bonding. Intermolecular forces. So the green is going to again be our proton donor, and the orange here is going to be our proton acceptor. Okay. So then we can use hydrogen bonding to help us understand and remember and never forget again ever why hydrofluoric acid is a weak acid, right? Hydrofluoric acid is not one of the strong acids. So a hydrofluoric acid molecule can do hydrogen bonding with another hydrofluoric acid molecule, and I've shown that here. So we have H bonding intermolecular forces. So the reason why hydrofluoric acid is actually a weak acid is because the hydrogen bonding intermolecular forces are so significant that they trap those hydrogens from ionizing to a great extent, right? You would think that strong acids, right, you put this in water and you get an H plus and an F minus. But what's actually happening in hydrofluoric acid is that this hydrogen here can't break away and become H plus. It's stuck between that fluorine and that fluorine. They're holding it very tightly. That's the reason why hydrofluoric acid isn't a strong acid, because it does not ionize completely. The final intermolecular force, and my personal favorite, is London dispersion intermolecular forces. Everything that has electrons has LDFs and is generally only significant when other intermolecular forces are absent. London dispersion forces are often considered the weakest of the intermolecular forces. So it goes ion-dipole, then hydrogen bonding, then dipole-dipole, and finally London dispersion is the weakest. LDFs arise from momentary distortions of an electron cloud with the creation of a very weak dipole. So again, this idea of dipoles comes back. But the momentary distortion of an electron cloud is really important. You're like, that's a lot of fancy words. What does that mean? So if we look on the left here, we have just a plano atom X, right, with its a little electron cloud around it. We know that these electrons are actually in what? Yes, you're totally right. Congratulations. Atomic orbitals. And we know that there are different types of atomic orbitals, S, P, D, F, theoretically G and H, right? And they have their own shapes, orientations, energies, all those unique things. But you'll notice that there is no dipole here. There's just like a nice even smattering of electrons, okay? But if we think about this example on the right, say we have two atoms X and they come near each other. So we have this atom X coming in and it gets closer and closer and closer and closer. Now what's happening is that the electrons here and the electrons here, they don't really want to be near each other because according to Coulomb's law, things with the same charge repel. So the electrons in this atom X, right, cause all the electrons in this atom X to kind of move away. So as it comes in closer, you'll see that it pushes those electrons away from it. But what happens when now these electrons get moved away from each other in this atom X here? So you'll see that we have a bunch of electrons over here and not so many electrons over here. Well, since we have more electrons on the left, we're going to accumulate a partially negative charge. So over here we have partially negative, over here it's partially positive, right? More electrons are accumulated on this side now than on this side. So what that did was that induced a momentary dipole, right? Because as soon as this atom X goes away, all the electrons here are just going to like redistribute and become normal. It's only when this atom X gets closer, okay? And so that momentary weak dipole is sort of like a fake dipole-dipole interaction, right? You'll get a positive wanting to get next to a negative. So this partially positive side in our momentary dipole likes being with the electrons in this atom X, just momentarily. And then as it moves away, everything goes back to normal. So you can also have ion-induced dipoles and dipole-induced dipoles, right? So as an example, right, we still have the neutral atom X, no dipole, just a nice even distribution of electrons. But when, say, for example, we have an ion that comes in, this negatively charged ion's going to want to get all of those electrons in the neutral atom X to go away from it. So this side becomes partially negative, this side becomes partially positive. That's because this negative ion is repelling all the electrons to the other side. And when it pushes all those electrons to the other side, you get a momentarily weak dipole. And so it's the same thing. The ion induced this dipole, so this is the induced dipole. Induced dipole. So an ion can induce that dipole, or another dipole could induce that dipole. So if you have a polar bond and the partially negative side comes in, it'll do the same thing. Induced dipoles are momentary. They'll go away. The induced means that something forced it. So like I induce, let's see, I don't know, like I induce you all to do homework by, I don't know, whatever. But so as another example of LDFs, if LDFs didn't exist, it would be impossible to liquefy diatomic hydrogen and nitrogen. The only intermolecular force that exists between two diatomic hydrogen molecules, molecule 1, molecule 2, is LDFs. They're nonpolar molecules. They don't have dipoles. There's no ions, right? All they have are these LDFs, these momentary induced dipoles. And so if we cool it down low enough, if we decrease the kinetic energy so low, these LDFs can dominate. They're going to take all those diatomic hydrogen molecules, they're going to hold them together at really, really low temperatures, and you'll transition from the gaseous phase to the liquid phase, where all those hydrogen atoms are a lot closer to each other, or hydrogen molecules are a lot closer to each other. So LDFs increase with increased polarizability. You're like, what is polarizability? Polarizability, if I can get my right highlighter size, polarizability has to do with how easy is it for those electrons to get moved around. Is it really hard? Is it really easy? You can think of it sort of like clay. If you let the clay dry, you can't really mold it. You can't move it around. But if you have really fresh clay, it's really easy to mold it and shape it. Same idea with electrons. If it's really polarizable, that means it's really easy to move those electrons around. Like here in the induced dipole, we moved all those electrons to one side. So LDFs increase with increased polarizability, and really what that is how many electrons are there. The more electrons you have, the greater the polarizability. So for us, as molecular weight increases, generally that means that you're going to have more electrons present. With more electrons present, that means that the polarizability is also going to be higher. Okay. The next consideration for LDFs is that the more linear a molecule is, the more linear a molecule is, the greater the LDFs will be, the more significant they will be. So as an example here, I have two molecules, and in both molecules I have 4 carbons. 4 carbons. And in this one I have 2, 4, 6, 8, 10, 2, 4, 6, 8, 10. Both of them have 10 hydrogens. So they're constitutional isomers of each other. So C4H10. Right? They are, you don't need to know the constitutional isomer. That has to do with organic chemistry as well. But anyway, so I hope you see that the molecule on the left is more linear. It looks more like a line. And the molecule on the right sort of looks like a little snowflake, kind of. So what happens is that if 2 of these linear molecules here on the left get near each other, as they approach, right, what happens is that you have that momentary polarization of the electron clouds like here, right? So this molecule approaches, it polarizes the electrons in that other molecule, and we get LDF interactions. And you'll see by the gray lines here that the area that interaction can occur is pretty big, like 2 long pieces of Velcro sticking together. Now, if we look at the molecules on the right, as this bottom molecule comes in, it will also do the same thing. It will also polarize the electrons in the top highlighted molecule. But understand, look at the gray lines here. The area that interaction can occur is a lot smaller. 2 really small pieces of Velcro. So with the Velcro analogy, imagine you have 2 long pieces of Velcro and you try and pull them apart, right? It's going to take a decent amount of effort. But then imagine you have 2 little bitty teeny pieces of Velcro stuck together, right? Not a very strong interaction. So the molecule on the right is going to have greater LDF intermolecular forces because it's more linear, meaning that there's a greater area for those LDF interactions to occur. And that is it. Thank you.